Hello everyone. Today we learn about the chapter 4 Field Effect Transistor FET Part 1. So the course outline, first we learn about the type of FET. Second is the comparison between BJT and FET. Third is the JFET. So the junction FET. And the last one is a junction FET characteristic and parameter. Field effect transistor FET, a three-terminal voltage control device used in application and switching application. So FET have a two type. First is JFET and the second one is a MOSFET. So FET is unipolar device depending solely on either electron or hole conduction. So for FET, an electric field is established by the charge present controlling the conduction path of the output circuit without the need for the direct contact between the controlling and control quantities. Basically, for FET, is a voltage control, which is the electron flow from the source to the drain, which is the gate as a controller. The type of FET, there are four types of FET. First is a junction field effect transistor, or we call it as a JFET. And another one is metal oxide semiconductor field effect transistor, or we call it MOSFET. So in MOSFET, I have two types. First is a depletion metal oxide field effect transistor, DMOSFET, and another one is an enhancement metal oxide field effect transistor, EMOSFET. In this chapter, we will cover the JFET and MOSFET only. The comparison between BJT and FET, we have a similarity. So BJT and FET as amplifiers, they also as a switching device. Another one is an impedance matching circuit. But they have a difference. FET is a voltage control, while BJT are current control device. FETs have higher input impedance, but BJT have higher gain, and FET are less sensitive to the temperature variation. Why? Because of their construction, they are more easily integrated on ICs. This is the symbol of BJT and FET, which has BJT have a collector, base, and emitter. So BJT act as a current control, but FET have a drain, gate, and source, where FET is a voltage control. So the JFET have a P channel and N channel. So there are three terminals of JFET. First is drain, gate, and source. So the JFET is like a water analog for the JFET control mechanism. So we have a source flow to the electron. So electron flow is from the source, which is controlled by the gate to the drain. So JFET symbols for N channel and P channel. N channel, the arrow is go to the source, but the P channel, the arrow is go outside to the gate. So N channel have a drain, gate, and source. P channel also have a drain, gate, and source. The JFET, like a BJT, control current flow. The transistor uses a current flow through the base emitter junction to control current. However, JFET uses a voltage to control the current. So voltage, BGG voltage level control current flow in the BDD RD circuit. So the current flow is from BGG. So the G is a gate. Gate can control the current flow. This is the behavior of the JFET. The current is controlled by a field that is developed by the reverse bias gate source junction. So gate is connected to the both sides. With more VGG or reverse bias, the field grows larger. This is a field or resistance limit the amount of current flow to RD. With low or no VGG current flow is at maximum. So that we can see that the more VGG, so the more voltage of VGG in the field grows larger, this field or resistance limit the amount of a current flow through RD. If VGG is higher, so they akan limitkan, they will limit to the current flow at the RD. This is the JFET. There are three basic operating conditions of JFET. First, if VGS equal to 0 volt, so VDS increasing with some value. But VGS less than 0 volt, so VDS at some positive value. And we call the JFET as the voltage control resistor. If a voltage VDD is higher or VGG is higher, so the resistor, the current to the resistor can lower. They can limit the resistor value. They can limit the resistor value, they can limit the current flow through the resistor. That is, we call it a voltage control resistor. The N-channel JFET construction and operation, we can see that the drain and the substrate between the drain and the N-channel, we call it ohmic contacts. So we have a gate, we have P-channel, we have a depletion region, and we have a source, the substrate between the source and N-channel, also we call it ohmic contacts. So the device consists of a channel of N-type semiconductor with ohmic contact at each end called the drain and the source. Alongside the channel are region P-type semiconductor electrically connected to each other and to the gate terminal G. So gate terminal G is a control device. So to control the voltage from drain to the source. So that the terminology here is depend on the depletion region and ohmic contacts. So the higher or the larger of the depletion region can influence the voltage of at the gate, or voltage of a drain, or voltage at the source. The junction between the gate and the channel is a reverse bias, so no current flow in the gate terminal. The greater the reverse bias, the thicker the depletion layer becomes. That I mentioned before. If the greater reverse bias, so depletion layer becomes the thicker. So the cross-sectional area of the conductive parts from the drain to source depend on the amount of a reverse bias between the gate and the channel. Therefore, the resistance between the drain and the source depend on the gate to the channel bias. So we call it the pinch-off voltage. This is an important parameter. Is the value of a gate to the channel bias required for the depletion region to extend completely across the channel. So for N-channel device, current flow into the drain, through the channel, and out of the source, because the resistance of the channels depend on the gate to the source voltage VGS, the drain is controlled by that voltage. So we can see that the drain D and the source S are connected to the N-type channel, and they get the two layers of P-type material. So we could use the water analogy to provide a sense for the JFET functionality. Water analogy to provide the sense. So means that the gate is a control the flow of electron from the source to get the drain until the drain. The source of water pressure can be treated like the applied voltage from drain to the source, which represent a flow of water, which is the electron from the speedon or source. The gate, through an applied signal, control the flow of water charged to the drain. Drain and source terminal here at the opposite. So we can see from the terminology to the JFET characteristic and parameters. Let's first take a look at the effect with the VGS of 0 volts. If ID increase proportionally with increases of VDD, means that VDS increases as BDD is increased. This is called the ohmic region. You can see at the point A to point B. We call it ohmic area. Why is ohmic area? Because ID increases proportionally with increases of BDD or BD BDS. So BDS increases, ID increases. Sorry, BDS increases, so ID increases. We call it mid area. The point ID chooses to increase regardless of BDD. So BDD increases is called the pinch off voltage point B. So when ID chooses the increases, maksudnya when ID is a stop increase, regardless the BDD increases, so we call the pinch off voltage. Pinch off voltage is to stop the IDD to increase more and more. This is a pinch off voltage. The current is called maximum drain current, IDSS. So when pinch off voltage is a stop, so we call that the current is IDSS. Pinch off stop to the ID to get more higher and more higher, and when the current is to be flat, so we call it IDSS. So at the breakdown C is reached when too much voltage is applied. This of course is undesirable, so JFET operation is always well below this value. From this set of curve, you can see with increased voltage applied to the gate, ID is limited, and of course the pinch of voltage is lowered as well. So when the ID is limited, so pinch off will go to the left to lower the value of the pinch off. So we can see in the mathematical equation, so we can see that ID equal to IDSS 1 minus VGS divide VGS off square. Sorry, VGS off bracket to power of 2. So the transfer characteristic curve illustrated the control VGS has on ID from cutoff, which means that VGS off to pinch off BP. Note the parabolic shape. The formula below can be used to determine drain current. So if the question give you the maximum current IDSS, and you have a VGS off and we have a VGS, so how you want to find the ID current, the real ID current? So the formula here is ID equal to IDSS times the bracket 1 minus VGS divide VGS off bracket to the power of 2. You can see from this graph. So if you know that if a BJT is IC equal to beta IB, means that I collector equal to beta current collector constant. So for JFET, the relationship between ID and VGS is defined by Shockley equation. So from the Shockley equation, we see that IDSS is constant and VGS is control variable. So this is a difference between JFET and BJT. If JFET, BJT, we have I collector equal to beta IB, but JFET is ID equal to IDSS bracket 1 minus VGS over VP to the power of 2. So I drain equal to I source, IC equal to IE. So I get equal to 0 volt, but VBE equal to 0.7 volt. You remember that Ig equal to 0 ampere. Sorry, Ig is equal to 0 ampere. VBE equal to 0.7 volt. So JFET, the gate is control voltage, but current at the gate is equal to 0 ampere. Thank you. Okay, the conclusion here is when between JFET and BJT is a JFET is a voltage control and BJT is a current control. So the mechanism here is a JFET is a more to the sensitive temperature. So we can see that JFET is designed for purpose for IC integrated instead of the BJT. So JFET, we can use the water analogy, means that gate as a controller to control the flow of electrons. So we talk about electron, we know that the electron is coming from the charge, so the flow of charge. When the flow of charge is the flow of current, so gate can control the flow of current from drain to source or from source to drain. Okay, thank you very much.